This is one of the most hotly requested topics for this channel. Even if you didn't actively request it yourself, you couldn't have missed the buzz around the James Webb Space Telescope. It is more powerful than any other space telescope, including Hubble. So big, it had to be folded up like origami to fit onto the rocket that carried it into space. So precise and sensitive, it has to be kept at temperatures not much warmer than absolute zero to prevent its own internal heat radiation from getting in the way of its sensors. So expensive, it cost $10 billion to make, and so complicated, it took decades to complete. 300 potential failure points stood between it and proper functionality. But now it is here. And it has an incredible mission: to study planetary systems for evidence of life, to understand the formation of planets, stars and galaxies, and to peer out across the universe to objects so far away the light they gave off has been traveling for almost as long as the universe is believed to have existed. In other words, the James Webb Space Telescope was built to spot the first stars and galaxies at the very edge of our knowable universe, objects from the beginning of time. And the first images have started coming in. I'm Alex McColgan and you're watching Astrum. Join with me on a journey as we look over the early photographs coming out of the James Webb Space Telescope and see for ourselves the power and precision of this engineering miracle. It's already promising to be spectacular. For those who are new to this channel, we've already spent some time watching the James Webb Space Telescope as it's gone from a work in progress to a fully realized piece of hardware. It was first conceived in the 1990s and was originally intended to cost only $1 billion and to launch in 2007. However, numerous setbacks and delays plagued the project, pushing it back again and again. It was only in December 2021 that it finally launched, and it has been spending the intervening months slowly unpacking itself, powering up its systems and testing its hardware. It is a 6,500 kilogram monster, with a sun shield whose 14 by 21 meter dimensions are around the size of a tennis court. Its mirror for capturing light is 6 times larger by area than Hubble's lens, which allows it to pick up more photons from further away to create crisp images. It boasts numerous cameras and scientific instruments which allow it to see across the infrared spectrum. This is a feature that is vital to its unique mission. Due to the expansion of the universe, all of the light from the furthest reaches of space have been stretched to the point that no matter what they were to start with, they are all at least infrared light now. So the only way to see these light sources is with an infrared telescope. On top of that, infrared is much better at punching through dust clouds and other obscuring debris, giving the James Webb Telescope the incredible ability to see objects that are beyond the sight of Hubble. I compare this telescope with Hubble a lot, as the James Webb Space Telescope was originally intended to be Hubble's successor. However, given their slightly different fields of view, Hubble can mostly see in visible light spectrums, while the James Webb Space Telescope can almost exclusively see infrared and can't see some visible light spectrums at all, it's more accurate to say that the two telescopes complement each other rather than compete. They work together to form a powerful duo, expanding our understanding of the universe. But that's not what you're here for. You're here to see what James Webb can do. Beginning in our own galaxy, let's gradually expand our vision outwards towards the edge of the knowable universe. You are in for some spectacular sights. The first stop on our journey is a place known as the Cosmic Cliffs. The Cosmic Cliffs, otherwise known as NGC 3324, are part of the Carina Nebula, about 7,600 light-years away from us. These peaks you are looking at are massive structures, around 7 light-years high, and what you see here is only a portion of the nebula as a whole. The actual nebula is much larger and contains a hollowed-out center, where the stellar winds given off by stars have blasted all nearby dust away from them. What we are looking at here is the edge of this hollowed-out bubble. Scientists are very interested in this region of space for one simple reason. It helps answer questions about the formation of stars. Thanks to the stellar winds in this zone, dust and matter conglomerate together, forming a birthing place for stars. However, for all our stargazing, there are still many mysteries surrounding this process. How exactly do they form? What do the different stages look like? It's difficult to tell. Part of the difficulty with finding the answers is the dust itself, both vital to the process and also a massive impediment to seeing it happen. It wraps around the forming stars like a protective cocoon, stopping scientists from seeing very clearly what is going on at the moments we'd like to see the most. James Webb fixes that. Not only does this image provide more detail than Hubble's image, but thanks to James Webb's onboard MIRI, or mid-infrared instrument, we can peel back the layers of dust and see what lies within. See how much clearer the image is. This will provide scientists with data on the formation of stars for a long time yet. So much for the birth of stars. At our next stop, the James Webb Space Telescope uncovers more about the end of their lifespan. And for this, let's look a little closer to home to NGC 3132, otherwise known as the Southern Ring Nebula. The image on the left was taken by James Webb's near-infrared camera, while the one on the right was taken by MIRI. This is a planetary nebula, although technically that term is a bit of a misnomer. While regular nebulas are the birthplace of stars, a planetary nebula is not a place planets form. Instead, it was just an unhelpful naming convention used by early astronomers who noted the round shapes of these nebulas and they thought they looked a bit like planets. The name stuck, even though our interpretation of the name has moved on. Planetary nebulas like this one are formed when dust and gas are blasted out from dying stars towards the end of their lifetimes. Knowing the chemical composition of this dust is useful, as understanding what material exists in the universe helps us to understand what later waves of stars might be made of. So once again, James Webb's ability to peel back the layers of dust to see what lies within is invaluable. Compare this with Hubble's image to get a sense of the increased detail that James Webb is able to bring to bear. From this, scientists have learned that the second star within the system still has not actually exploded, so the formation of its own planetary nebula is still likely to come. We can also get a better sense of how the gravitational interactions of the two stars stir the nebula, mixing the dust together in fascinating patterns. Now, let's look a little further out, beyond our galaxy. If we want to see star creation, it makes sense to find a location like this. 161,000 light-years away from us lies the Tarantula Nebula, so named because it evokes the idea of a giant tarantula lurking within its silken web. Aside from the obvious otherworldly beauty, this area is of particular note to scientists because of its similarity to a period in the universe's history known as the Cosmic Noon. At that point, which to our best understanding took place about 1 billion years after the universe began, star creation was at its most prolific. It is thought that conditions there would have looked something like this. James Webb has been able to spot stars here that are only just coming into being, a fascinating period of time to study. Let's look further out again. As our gaze extends, we lose track of individual stars and start seeing things on a galactic scale. Even here, there are beautiful dances being played out. Stephan's quintet is a formation of 5 galaxies, although one is not really next to the others, but just looks that way from our perspective. Famous for being featured in the film It's a Wonderful Life, it is thought that 4 of these galaxies will one day collide. Indeed, 2 are already doing so. James Webb allows us to see clearly the brilliantly hot dust being kicked off as these 2 central galaxies circle each other. The gravitational forces here are mind-bogglingly intense, the energy profound. It is a dance that is truly only appreciable at scales like this one. This image was not taken at a single time, but actually is a composition of almost 1,000 separate images that James Webb took and then scientists put together, giving it incredible resolution for picking out details. Let's look further out again. Until even James Webb is straining to see, in an image known as Webb's first deep field. This image is taken from an area so small, a single grain of sand held out at arm's length would block it from your view in the night sky. At this scale, individual stars are almost completely absent. Most of what you can see here are not stars, which would be too small to detect on their own, but galaxies. Here you can see the fish lens effects being created by gravitational warping, as relatively nearer objects bend light around them, distorting what lies beyond. We start to see the edges of the universe. In this image is one of the oldest galaxies we have ever sighted. It is so far away, the light from it, when it was born at the beginning of the universe, has only just reached us. Where is it? We are going to need to zoom in. Do you see it? It's admittedly quite small. By evaluating markers within the light given off by this tiny red galaxy, scientists are able to identify how far it has redshifted, and thus how long the light from it has been traveling by comparing it to normal visible light from similar sources. This tiny dot was found to be 13.1 billion light years away. As far as we know, given that the universe is thought to be 13.7 billion years old, this is one of the earliest galaxies that we will ever be able to see. Now, you might be disappointed by how small it is. However, there is some room for hope. Compare this image with one taken by Hubble of the same region. Obviously, James Webb's image is crisper and clearer, giving more detail and showing more objects. But there is one vital distinction between these two images. Hubble took its image by staring at this patch of sky for 10 days, slowly gathering every photon it could from this region of space and compiling them into a single image. James Webb, on the other hand, took only half a day taking its own image. What this implies is that if James Webb was able to take such a detailed image in 1/20th of the time, imagine how detailed an image it could take if it was given a comparable amount of time. In other words, this tiny little dot is likely not the best that James Webb can do. I hope these images have given you a sense of the scientific breakthroughs possible with the James Webb Space Telescope, but also just how beautiful the sights of the universe are. Images like these blew me away. Sadly, we are going to have to be a little patient to see what discoveries James Webb might have in store for us. James Webb has only just finished running through its calibrations, letting its instruments cool off and making sure everything is working perfectly. There are queues of scientists fighting over who gets to use it to do what over the next 5 to 10 years of its expected lifespan. Each second is hotly contested. It will be investigating exoplanets for signs of hospitable atmospheres for life, unveiling nebula to find the origin of stars, and will help us to understand the difference between an old galaxy like ours and the young galaxies that formed just after the Big Bang. With a tool as powerful as the James Webb Space Telescope, who knows what else we are about to discover. To walk outside at night and peer into the glittering darkness of space is a special experience, but one that doesn't capture the true majesty of space and everything it contains. Light pollution, atmospheric distortion, and our limited eyesight prevent us from truly exploring the universe and discovering its secrets. Thankfully, the Hubble Space Telescope, from its position orbiting around 550 kilometers above Earth, allows us to overcome these limitations and see deep into space, changing our understanding of astrophysics and shaping our knowledge of the universe, while also dazzling us with remarkable images. I'm Alex McColgan, and you're watching Astrum. Today we're going to look through the Hubble telescope, take a journey billions of light years into space, and explore and give context to the furthest reaches of our galaxy and far, far beyond, all the way to the most distant object ever seen. What will we see along the way, and what will Hubble surprise us with in this episode? Our first encounter is 3,800 light years away, where we see vast blue wings stretching out into space. But what is it? This is NGC 6302, otherwise known as the Butterfly Nebula. Lying within our Milky Way galaxy, the Butterfly Nebula's spectacular array of blue and turquoise colors is actually the glowing gas that was once a star's outer layer. The wing shape showcases the expansive journey that this gas has taken over the last 2,200 years, covering a distance of over 2 light-years. Recent observations of the Butterfly Nebula have detected unprecedented levels of intricacy in the gas jets and bubbles erupting from the star at the nebula center, all of which create rapid changes in the wing shape you're seeing now. Traveling beyond to 8,000 light-years away, we find the star cluster Pismis 24. This cluster contains a combination of remarkable phenomena. First, your eye will be drawn to the core of Large Emission Nebula, rising up and glowing. Second, you will notice the blue stars lingering in and around the nebula. These blue stars owe their blue color to their intensely hot temperature, far hotter than our own sun. This is due to their mass, which determines the temperature of a star, with blue stars having at least 3 times the mass of our own. These blue stars help to give Pismis 24 its signature color and texture. Their extreme ultraviolet radiation causes the gas surrounding the cluster to heat and bubble around the star in remarkable clouds, which makes probing the region extremely difficult. For a while, Pismis 24-1, a star in the Pismis cluster, was thought to be the most massive star ever recorded at almost 300 solar masses. However, it is now thought to be at least 3 stars, each weighing in at almost 100 solar masses. Much smaller than originally thought, but still some of the largest stars ever recorded. Pismis 24 is part of the diffuse nebula NGC 6357, a cosmic nursery. The nebula is home to many protostars shrouded by dark gases. Protostars are the earliest stage of stellar evolution, where stars gather mass from their parent molecular cloud. Alongside these protostars are many young stars encased in expanding cocoons of gas, making the nebula feel like a living organism. Now let's go even further. Journeying 60,000 light-years away, we come across Palomar 12, with its globular cluster of stars hanging in deep space. Lingering on the outskirts of the Milky Way's halo, these stars are around 30% younger than the other globular clusters in the Milky Way galaxy. What is the secret to their young age? They were abducted. Palomar 12 isn't actually from the Milky Way galaxy, but from the Sagittarius Dwarf Elliptical Galaxy. Around 1.7 billion years ago, the Palomar 12 cluster was torn from its home galaxy by tidal interactions with the Milky Way. In fact, Palomar 12's home galaxy is currently being ripped apart by our galaxy. These tidal forces are limited to the immediate surroundings of their respective galaxy, but when they collide or pass nearby one another, the results are striking, creating strange, distorted shapes, or unique phenomena as demonstrated by Palomar 12, where clusters born in one galaxy end up living in another. Our journey doesn't end here. Hubble allows us to see much further. Let's continue our voyage outwards, hopping more quickly between locations, starting with 30 million light-years distance, where Hubble allows us to see a familiar view from a new angle. This is the Sombrero Galaxy. As we see it from the side, it shows us the flat, disc-like shape of most galaxies, a view we don't typically see. You might be wondering why this flat shape is the norm. After all, planets, moons, and meteors tend to be spherical. Shouldn't all galaxies be the same? The reason for the more common flat shape found in galaxies is that, as mentioned before, the universe is in constant motion, and gravitational forces caused by the black holes at the center of galaxies cause them to rotate, with the conservation of angular momentum leading to an outward disc-like shape. The Sombrero Galaxy is notable for the blinding white core at its center, and the distinct lanes of cosmic dust spiraling outwards, the most pronounced of which linger at the rim, giving the galaxy its distinct sombrero shape. Continuing further, at 65 million light-years, we see the broad elliptical galaxy NGC 1052-DF2. Do you notice anything distinct? You might have spotted its particular diffuse texture, so diffuse in fact that distant galaxies can be seen behind it. This gives the galaxy a supernatural, almost ghostly appearance. But the most strange of all is that this galaxy is possibly missing all of its dark matter. This was the first galaxy of its kind to display such an absence. As for why, we're not truly sure. Let's go even further, this time just over 300 million light-years from Earth. This is the Coma Cluster, a large gathering of more than 1,000 galaxies, all linked together by gravity. A cluster that also happens to be one of the first places where we discovered indications of dark matter. In this image that you're looking at, you can see thousands of intra-cluster globular clusters. These are spherical groups of stars that are not bound to a galaxy, but to the Coma Cluster itself. While this might seem far, we can travel even further. Over 9 billion light-years away is Max J1149, aka Icarus, once the furthest star we knew of in the universe. In fact, light from Icarus takes so long to reach us that it appears to us the same way it did when the universe was 30% of its current age. To give a sense of how far away Icarus is, at the time of its capture in this image, Icarus was at least 100 times further away from the nearest star. Yet we can travel even further, to distances that seem beyond comprehension. Nicknamed Earendel, WHL0137-LS is a star in the Cesus cluster whose light took over 12.9 billion years to reach us. However, due to the expansion of the universe, the distance between Earendel and ourselves is now even greater, 28 billion light years. We are just seeing it where it was almost 13 billion years ago. Earendel is suspected to be 50 to 100 times the size of our Sun, and due to its enormous mass, is expected to explode in a supernova in a few million years from our perspective. Nicknamed Earendel after the Old English name for morning star or rising light, the name is actually a reference to J.R.R. Tolkien's character Earendel, who travelled through the sky carrying a jewel as bright as a star. Outside of its interesting name and impressive size, Earendel also has an effective surface temperature of at least 20,000 Kelvin, almost 4 times hotter than our Sun. There is also a small possibility that it is a population 3 star, which means it would contain almost no other elements beside hydrogen and helium, and it would be far brighter than your average star. We are able to see this star through an effect called gravitational lensing, where a cluster of galaxies warp light from the star around them in just the right alignment so that they act like a huge lens, allowing Hubble to see much further than it otherwise would have been able to. Things are so unbelievably far away now that even Hubble is reaching its limits. But is there anything further that we can see on our journey to the far reaches of space? Yes. There is one more object Hubble can show us, the redshift galaxy known as HD1, the earliest and most distant known object in the observable universe. Although little more to us than a faint red dot, HD1 is actually 13.5 billion light years away, or at least it was when the light was emitted. It is estimated to now be at a distance of 33.4 billion light years away with the expansion of the universe taken into account. While it lies at the very reaches of our perception, it has some telling details. Its extremely luminous ultraviolet emissions suggest it could be a starburst galaxy, producing stars at an unparalleled rate. It could also be home to the enormous population 3 stars described moments ago that are far more luminous than the stars we are familiar with. However, these and any other theories are speculative due to the minimal amount of photons we are working with. All we do know for sure is that something is out there 33.4 billion light years away, and for now, that's the furthest thing that we can see. To get more information, and perhaps even further views of the universe, we will need the James Webb Space Telescope, the most powerful infrared telescope of all. But until then, let's be thankful for the sights Hubble has shown us, and the 33 billion light year journey it has allowed us to take. and what a journey it is. In the dark, frigid void beyond Neptune lies a vast and mysterious region where the ancient remnants of our solar system's birth drift silently through the darkness, perfectly preserved by the deep freeze of space. To reach this shadowy expanse from Earth, we must travel past the rocky planets, flying by Mars and then beyond the swirling storms of Jupiter and Saturn. Farther still, out beyond the blue giants, Uranus and Neptune, we finally reach our destination. Welcome to the Kuiper Belt, a vast ring of icy debris encircling our solar system like a frozen halo. This isn't just a collection of distant rocks, it's a time capsule from 4.6 billion years ago, holding the untouched building blocks of our cosmic neighborhood. It is home to several dwarf planets and mysterious objects that have left many astronomers scratching their heads. I'm Alex McColgan and you're watching Astrum. Join me today as we explore the worlds lurking in the shadows of our solar system and piece together clues about its history, about planetary formation, comet activity, and even the origins of life. Before we knew for sure that the Kuiper Belt was real, astronomers suspected that something existed beyond Neptune. For decades, everyone's favorite dwarf planet, Pluto, was thought to be an isolated object in the outer solar system, but something didn't add up. Its small size and unusual orbit suggested that Pluto wasn't alone, and that maybe it was merely one of a number of yet-to-be-discovered distant objects. In 1951, astronomer Gerhard Kuiper predicted the existence of a belt of icy objects just beyond the orbit of Neptune, but without telescopes powerful enough to detect these objects, the idea remained theoretical for decades. That changed in 1992, when astronomers David Jewitt and Jane Liu discovered the first confirmed Kuiper Belt object, known as 1992 QB1. Pluto and its moon Charon were both discovered before 1992 QB1, Pluto in 1930 and Charon in 1978, but these objects were only confirmed as KBOs after the 1992 KBO. Since then, thousands more Kuiper Belt objects have been identified, populating this distant region beyond Neptune. To grasp the true scale and position of the Kuiper Belt, let's imagine we're traveling in a spaceship, starting from the Sun and moving out towards the outer edge of our solar system. As we move along our journey, let's compare the Kuiper Belt to both the more well-known asteroid belt and the less well-known Oort cloud. Starting near the Sun, we zip past the rocky planets, Mercury, Venus, Earth, and Mars. Between Mars and Jupiter, we see the asteroid belt, made up of the leftover materials from when our planets formed. A thin, spread out ring of rocky debris, the asteroid belt is about 2.2 to 3.2 astronomical units away from the Sun and about 1 astronomical unit wide. As a reminder, 1 astronomical unit is equivalent to the distance from the Sun to the Earth. Most of the known asteroids reside in this part of our solar system, ranging in size from the largest asteroid, Vesta, at 525 kilometers wide, almost the distance from London to Belfast, to the smallest objects, some of which are just tens of kilometers across. However, despite residing in such a large space, the total mass of all of the asteroids in the whole asteroid belt combined is only about 3% of the mass of the Moon. Beyond the asteroid belt, we encounter the gas and ice giants, Jupiter, Saturn, Uranus, and Neptune, colossal worlds that dominate the outer solar system. Finally, as we pass Neptune's orbit at 30 astronomical units, we reach our destination, an even more remote, icy frontier, the Kuiper Belt. This vast expanse stretches from 30 to 50 astronomical units, and is home to a range of intriguing objects, from frozen relics of the early solar system to dwarf planets including Pluto, Haumea, Eris, Makemake, and countless other smaller objects. Like the asteroid belt, the Kuiper belt contains ancient debris from our early solar system. In fact, Kuiper belt objects are considered some of the oldest surviving pieces of our solar nebula that originally formed the planets of our solar system. And so, at one point in the very distant past, these stray pieces might have been able to come together to form yet another planetary body. However, Neptune's gravity prevented the icy objects from coalescing and never allowed them to form something new. Unlike the asteroid belt, which is primarily made of rocky material, the Kuiper belt consists of mostly frozen methane, ammonia, and water ice, forming a frozen, thick, donut-shaped ring of debris. The Kuiper belt contains hundreds of thousands of large icy bodies bigger than 100 kilometers across, and more than 1 trillion comets, not to mention smaller debris and dust. And the average distance between objects is so large it can be hard to imagine. Each of those objects is, on average, between 0.02 to 0.1 astronomical unit apart. Imagine 10 million kilometers between objects. Here in the dim outer reaches of our solar system, these icy bodies drift in near silence, preserving vital clues about the origins of planets and comets. But it doesn't end there. That was just the main region of the Kuiper belt. Overlapping the outer edge of the main region is another area of Kuiper belt called the scattered disk, which continues out to nearly 1,000 astronomical units, with some Kuiper belt objects on orbits that reach even farther beyond that. So while the asteroid belt and Kuiper belt share some similarities, as you can see, one is vastly more expansive than the other. And while we may have reached the end of the Kuiper belt, there's still another massive structure that surrounds every other object and belt I've mentioned so far. In a recent video, I talked about the Oort cloud, the colossal structure of orbiting icy debris that encircles our entire solar system. It's so jaw-droppingly far away that even our most powerful telescopes can't catch a glimpse. So how do those two structures, the Oort cloud and the Kuiper belt, differ from each other? For one, the Kuiper belt is thousands of times closer to the Sun than the center of the Oort cloud, which is theorized to stretch from 2,000 to 100,000 astronomical units. Another major difference is that the Kuiper belt is donut-shaped, while the Oort cloud is spherical, like a gigantic bubble of swarming debris. But something these structures do have in common is that they are both sources of the celestial phenomenon that we know as comets. The Oort cloud is the source of many long-period comets, while the Kuiper belt is where some short-period comets are born. While the Kuiper belt today is one of the most massive structures in the solar system, it's just a small fraction of what it once was. Originally, altogether, it probably contained 7 to 10 times the mass of Earth, but the shifting orbits of the 4 giant gas and ice planets caused most of that to be lost to space. What remains is no more than about 10% of Earth's mass. Not only that, but the Kuiper belt today continues to slowly erode away. As objects occasionally collide and break apart, smaller fragments are left in their wake, and some of the resulting dust is blown out of the solar system by the solar wind. Sometimes these collisions, or Neptune's gravity, will cause Kuiper belt objects to head on a new path towards the Sun, creating short-period comets which have orbits of less than 200 years. Over time, the Sun's radiation causes comets to shed material, producing the spectacular tails we see from Earth. Several famous comets originate from the Kuiper belt or its scattered disk, including Halley's Comet with an average orbital period of 76 Earth years, or Comet Shoemaker-Levy 9, which broke apart and smashed into Jupiter in 1994 in the first ever observed collision of 2 solar system bodies. As we all know, Jupiter survived, but the impact was visible from Earth and was quite a spectacular sight to behold. You can see it out for yourself if you check out my video on the aftermath of this collision. You may also have heard in the news recently about a near-Earth asteroid named 2024 YR4. While there is a very, very small chance of this asteroid colliding with our moon, or even a smaller chance of it impacting Earth, the short-period comets originating from the Kuiper Belt pose no immediate threat to us in the next 100 or more years. In other words, you don't need to worry about that. Despite the Kuiper Belt being just a small remnant of what it once was, it still offers a nearly endless frontier of objects for us to explore. And unlike the Oort cloud, which we have not been able to visit yet, we have been to the Kuiper Belt. While most of what we know about the Kuiper Belt comes from ground-based telescopes and the Hubble Space Telescope, NASA's New Horizons is the only spacecraft to have actually been there. It performed a flyby of the dwarf planet Pluto and Kuiper Belt object 2014 MU69, which was later officially named Arrokoth, meaning sky, in the Native American Powhatan or Algonquian language. This flyby of Arrokoth in 2019 was the most distant flyby in the history of space exploration, taking place 1.5 billion kilometers beyond Pluto, with the New Horizons spacecraft getting as close as about 3,500 kilometers above the surface of the object. And even among the swarm of mysterious objects that make up the Kuiper Belt, Arrokoth still managed to surprise the New Horizons team. Its strange shape was unlike anything we had ever seen in our solar system. Arrokoth is a small icy KBO known as a contact binary, composed of two distinct lobes that at some point merged into one body. Its shape resembles a flattened snowman. At just 35 kilometers long, 20 kilometers wide, and 10 kilometers thick, you might not think there's much to learn from this relatively tiny object. But what Arrokoth lacked in atmosphere and diverse geology, it made up for in its unique structure. The bizarre pancake snowman shape of this Kuiper Belt object provides crucial insights into how planetary building blocks came together in the early solar system, and how planets may have formed. Arrokoth's shape seemed to give it a counterintuitive gravity field and rotation, and several papers published since the flyby have led to an almost undeniable truth about how planetesimals form, something the New Horizons team didn't expect. Planetesimals form when smaller objects come together to make larger bodies, which may eventually combine to create a planet. Until now, there have been two competing theories: hierarchical accretion, which proposed that small objects would crash into each other at high speeds until they created something bigger, and local cloud collapse, where nearby objects would slowly come together because of their gravitational attraction, thereby forming larger and larger bodies. And now, thanks to the Arrokoth flyby and important research into the object's geology, geophysics, composition and formation, we can be fairly certain that the theory of local cloud collapse is correct. The object's smooth surface and the lack of fractures from stress confirm that the cosmic snowman formed at low speed. Alan Stern, a planetary scientist and the lead for the New Horizons mission, said that the evidence was so strong, we've decisively solved a multi-decade debate about how planetesimals form. And thanks to New Horizons, we get to see the most famous Kuiper Belt object, Pluto. The spacecraft performed a flyby in 2015, allowing us to get up close and personal like never before and take those stunning images. The mission collected observations of Pluto and Charon, the dwarf planet's largest moon, and was able to collect data on Pluto's other satellites, Nix, Hydra, Kerberos, and Styx. Of course, we've all seen the stunning photographs of Pluto's heart-shaped surface region, also known as Tomba Regio. But did you know that the heart-shaped feature is actually a glacier? The western lobe of the heart, named Sputnik Planitia, after Earth's first artificial satellite, Sputnik 1, is a vast nitrogen glacier that stretches 1,000 kilometers wide and 4 kilometers deep, and is undoubtedly the largest known glacier in the solar system. The eastern lobe of the heart gets its light color from nitrogen that is carried from Sputnik Planitia and deposited as ice. Not only did we get stunning images of Pluto, but the data from New Horizons forever changed how we understand our favorite dwarf planet. It revealed that Pluto is far more complex than we previously thought, and offered clues to the origin of its heart-shaped feature. The data led some to believe that Pluto's heart-shaped region could be explained by an internal water-ice ocean. However, a recent study led by astrophysicist Harry Ballantyne from the University of Bern has revealed another, more likely culprit. The heart shape may have been caused by a low-velocity impact that left a gigantic splatter across the surface of Pluto, creating the western half of the heart shape. This impact would have come in at an oblique angle, as in not straight on. Imagine throwing a water balloon across dry pavement in the same way you might skip a stone across a pond. When the balloon scrapes the pavement, it pops, leaving an elongated splat of water across the pavement. This kind of angled, low-velocity impact is similar to how the western lobe of Pluto's heart feature may have been created. But it's not just Pluto that we get to see up close. The images of Pluto's moon Charon were also incredible. Can you make out the enormous equatorial tectonic belt? Its existence suggests a long-gone water-ice ocean on Charon. So what comes next in our quest to understand the Kuiper Belt and, consequently, to understand our solar system? New Horizons is expected to exit the Kuiper Belt sometime between 2028 and 2029. And while there is no current target for a further flyby, it is possible that NASA identifies another suitable target. New tools like the James Webb Space Telescope could help us to further analyze the composition of Kuiper Belt objects. And perhaps in the distant future, a robotic mission might allow us to land on one of these mysterious objects, or even collect a sample for a return mission back to Earth. Who knows what else we'll discover out there in this vast, frozen frontier? As technology advances, future missions will hopefully push deeper into the Kuiper Belt, revealing more of its long-held secrets, one icy world at a time. In 1977, two pioneers embarked on what might be one of the most epic feats of exploration ever undertaken. Their goal? To unravel the cosmic mysteries surrounding the solar system and our place in it. Not only did they provide us with some of the first and best imagery of our solar system's outer planets, but they continued to send us incredible new information about our universe from interstellar space, some 47 years and 24 billion kilometers later. The Voyager 1 and 2 probes are more than just instruments and circuitry. They are a symbol of humanity at its best. Curious, audacious, ambitious, and resilient. Voyager didn't just capture dazzling photos of our gas giants and their moons. It captured the hearts and minds of generations back home on Earth. These are the probes that have gone the furthest that any human object has traveled. They are trailblazers and groundbreakers. It is their unique opportunity and their peril to travel beyond the reach of humanity, to capture images of things we have never seen before so close up, nor have we seen since. When I look back, I realize how little we actually knew about the solar system before Voyager, says Voyager mission project scientist Edward Stone. We discovered things we didn't know were there to be discovered, time after time. So, are you curious to see what they learned? I'm Alex McColgan and you're watching Astrum, and in today's Supercut we'll cover everything you might ever want to know about the Voyager missions, from the probes themselves, their grand tour, to their impending tragic finale. It's one of life's little ironies that it is not new, cutting-edge technology that is advancing our understanding most at the edge of our solar system, but old machines. They have an onboard computer with less memory than the one inside your car's key fob. To this day, they are still using 8-track magnetic tape from the 1970s, which makes them older than many of you sitting here watching this. This is the conundrum of deep space exploration, where vast distances and extremely long travel times can mean that technology is antiquated by the time it has reached the most ambitious targets. Of course, Voyager 1 and 2 were not initially meant to travel all the way to interstellar space. They were instead built for a 5-year mission to explore Jupiter and Saturn and their larger moons, which was only possible thanks to a rare, once every 176 years planetary alignment. However, after completing all of its initial objectives on Jupiter and Saturn, the Voyager mission team added flybys of Uranus and Neptune to one of the probe's objectives. Later, these too were completed, so NASA announced the start of the even more ambitious Voyager interstellar mission, with the purpose of exploring the outer limits of the Sun's sphere of influence and beyond. This final journey would take both probes off the ecliptic to unexplored parts of the solar system, such as the termination shock and the denser and hotter heliosheath, before finally crossing the heliopause into interstellar space. But how did these incredible machines manage to accomplish so much beyond the scope of their original mission? It all comes down to that old but incredibly effective technology. NASA scientists made a number of forward-thinking design choices that allowed the probes to far exceed their initial objectives. To put it simply, they were built different. Here's how. Let's start with one of the most consequential decisions, the fuel source. Each probe is equipped with a long-lasting radioisotope thermoelectric generator, which converts heat from the decaying plutonium-238 isotope into electric power. These generators were capable of producing 157 watts of electrical power upon takeoff, about enough to power a laptop and maybe charge a mobile phone too. This might not sound like much, but was more than Voyager needed. While a radioisotope generator meant that power production was in constant decline, it would half in strength every 87.7 years, it would still be enough power to keep the essentials on the probes running until at least 2025. This long-term fuel capacity was no accident. You see, when the Voyagers launched in 1977, NASA faced a unique opportunity. The planets would soon be in that 1 in 176 year alignment that had last occurred during Napoleon's first reign. This rare alignment would not only allow the Voyagers to visit Neptune and Uranus with minimal course adjustment, but also give the probes a gravity assist from each of the 4 outer giants they visited, thereby increasing their effective velocity beyond what they could get from their own rocket propulsion. This idea was relatively new at the time, having been only attempted previously on NASA's Pioneer missions to Jupiter and Saturn. However, this narrow window gave NASA a strict deadline. There wasn't enough time to plan follow-up missions, and the United States Congress wouldn't earmark enough funding for a longer expedition, like the Grand Tour NASA first proposed. So, what did Voyager's team do? They devised a series of engineering feats to optimize the probes for a potentially longer mission and fervently hoped that the funding would follow. Each of the Voyager probes is equipped with 11 scientific instruments. Most of them have redundancies in case of machine failure, which can be toggled on and off to conserve power. To adjust course and orientation, the probes are equipped with gyroscopes for stabilization, referencing instruments, and 16 hydrazine thrusters, including 8 backups. Backups, and good backups at that, were key to the Voyager probe's longevity. They proved to be vital, as Voyager 2's main thrusters stopped working after 37 years. Its backup thrusters had to engage after 4 decades of idleness. And guess what? They worked perfectly, highlighting the excellent engineering that went into them. The Voyagers also have custom-built onboard computers, which are antiquated by today's standards, but were cutting edge in 1977. The probe's wide-angle and narrow-angle lens cameras are controlled by a computer command subsystem, which has fixed programs like fault detection and correction routines. Another key to its success lay in its computers. Each probe had a computer called the Attitude and Articulation Control Subsystem. And no, it doesn't scold the Voyagers when they get sassy. Attitude refers to probes' orientations with respect to the Earth, without which their high-gain antennae would be unable to send or receive signals from NASA's Deep Space Network. This is very important, as the probe's transmitters only have the wattage of a refrigerator light bulb, and at such immense distances, their radio signals become barely detectable whispers. To communicate with the Voyager team and vice versa, the probe's antennae must be facing the Earth, and the Deep Space Network must in turn know exactly where they are. Otherwise, they would be lost, like a needle in a 287 billion kilometer haystack. Each Voyager spacecraft has a 3.7 meter antenna for real-time transmission and an 8-track digital tape recorder capable of buffering 536 megabits for future transmission, enough to store 100 photographs. While this was still a huge step up from the earlier Pioneer probes, which had no onboard data storage, it's still a fraction of what the smartphone in your pocket can store today. Despite these limitations, the DTRs were built to last. Odetics, which manufactured them, claimed that their DTRs could process over 4,000 kilometers of tape without taking visible wear and tear. They had to withstand the harshest environments imaginable and undergo rigors that had never before been tested. Yet, the Voyager DTRs performed without data loss or machine failure until they were finally taken offline to conserve power. Not bad for machines 12 years older than the World Wide Web. Durability was a chief concern during Voyager's planning. There are many unknowns in a mission of this magnitude. To get to Jupiter, both Voyagers would have to pass through the asteroid belt. Scientists once believed that this region would shred apart any spacecraft that tried to pass through it. However, Pioneers 10 and 11 had previously been able to pass through the asteroid belt, which emboldened Voyager's team to repeat the stunt. However, failure would have meant disaster before the probes had even reached their first target. Luckily, both probes made it through the asteroid belt unscathed, and we now know that it is mostly empty space thanks to them. Even with all these successes, and with the probes performing far better than their engineers could possibly have hoped for, as the two spacecraft traveled through the vastness between the planets, there was still at least one more hurdle to cross. What would happen to the probes in the extremely cold temperatures of interstellar space? NASA installed multiple heaters to keep the machinery operational. Nonetheless, as the probe's power waned, NASA had to turn off some of their heaters to conserve energy. When the Cosmic Ray Detector's heater was turned off 2 years ago, its temperature plummeted by 70 degrees Celsius. Needless to say, sending a repair team 23 billion kilometers into space isn't an option. So everyone thought the instrument would break, but it continued to run smoothly. The fact that the probes have operated so well for 45 years is a testament to their resilience and engineering. But with all this technology, what did they see? Let's go back to the beginning and follow the path they blazed across our solar system. On the 20th of August 1977, NASA launched the Voyager 2 space probe from Cape Canaveral, Florida. Its partner in crime, Voyager 1, was launched 2 weeks later on the 5th of September. Even though both probes were Jupiter-bound, Voyager 1 was set on a shorter, faster trajectory, so taking off second made sense. It overtook Voyager 2 on the 15th of December 1977 and exited the asteroid belt first. Together, this dynamic duo was set to take a dazzling parade of pictures that were absolutely revolutionary at the time. But don't take my word for it. Let's jump in and you'll see for yourself. 13 days after launch, Voyager 1 sent this photo back to Earth. The first of tens of thousands it would send back over the next 5 years. Taken 11.6 million kilometers from Earth, it's a sentimental place to start our journey. It might remind you of the Earthrise photo taken by the Apollo 11 crew from the moon just 8 years prior. We can see our blue marble and its moon in the distance. I don't know about you, but I find this photo so hauntingly beautiful, especially knowing how far this probe had travelled and how much it's seen since then. But we've got a long way to go, so let's move on. It would be almost 2 years before Voyager 1 finally makes its approach to its first target, Jupiter. Not bad, considering it's 714 million kilometers away. Voyager 1 arrived first on the 5th of March 1979. You see, it travels at 17 kilometers per second, 2 kilometers per second faster than Voyager 2, who, despite leaving Earth first, arrived 4 months later on the 9th of July 1979. This is because the trajectory Voyager 1 took allowed it to gain more speed relative to the Sun. Now, Voyager 1 was not the first spacecraft to encounter Jupiter. That was Pioneer 10, 7 years prior in 1972. And while the Pioneer mission certainly provided great scientific insights, it didn't quite grab the imagination of the public. But sending back stunning images like this, Voyager certainly did. This is Jupiter in all its glory. It's kind of hard to accept that these are actual photos and not paintings or some AI-generated image. If you look closely, you can spot 2 of its moons, Io on the left and Europa, the beige one, on the right, but more on them later. Luckily for us, Voyager 1 even recorded its approach to the great gas giant. It took photos at regular intervals, every 10 hours, or 1 Jupiter day. This means the planet is in the same point of its rotation in all the photos. The 66 photos were spliced together to create this time-lapse movie, spanning Voyager 1's approach to Jupiter from the 6th of January to the 3rd of February 1979, covering a distance of 27 million kilometers. I personally can't decide if it is incredible or terrifying. But let's get a closer look and see what surprises this planet is hiding. Something that immediately stunned scientists was Jupiter's atmosphere. They expected to see east-west and west-east winds in Jupiter's different atmospheric zones, but what caught them by surprise was the amount of turbulence, plumes, and rotational movement, which are super clear in this image. You can immediately see how dynamic the atmosphere of Jupiter is. Scientists had already suspected Jupiter's most notable characteristic, its Great Red Spot, might be a counterclockwise rotating formation. Not only did Voyager data confirm this, it also showed a surprising amount of similar phenomena in other parts of the atmosphere. The white spot you see below the Great Red Spot is one example of these surprise storms. Turns out Jupiter's atmosphere is littered with them, and we had no idea. When we think rings, we think Saturn, but thanks to Pioneer data, scientists have long suspected that the same is true for Jupiter. Voyager data not only confirmed the existence of 4 Jovian rings, it was also the first to image them. This picture taken as Voyager leaves Jupiter highlights the rings beautifully, as that glowing orange line protruding from the planet. Before we leave Jupiter and continue our journey, I did promise we would come back to its moons, Io and Europa. Possibly the biggest shock from the Voyager expedition is the discovery of volcanic activity on Jupiter's moon, Io. Prior to Voyager, geologists thought Io would be covered with large impact craters, like our own moon. While they did find circular markings on Io's surface, they didn't appear to be from craters. The dark spots you see indicate the presence of volcanic hotspots and lava lakes. This photo shows lava flow from less than 1 million years ago, which is incredibly recent and totally unexpected. We now know Io as the most geologically active site in the solar system. At the time of these images being taken, it would have been incredible to capture Io mid-eruption. Imagine expecting to see a moon similar to ours, then stumbling upon a sight like this. These blue explosions on the surface of Io shot material and gas 100 kilometers into space. The volcanoes are incredibly active, going off relentlessly every few hours, treating Voyager to several jaw-dropping photos. The next moon out from Io is Europa, and it could not be more different. An icy world. Voyager 1 was the first to show us that Europa is covered by curious scratch markings. Scientists suppose them to be some type of ice fracture patterns on Europa's surface. It was also Voyager data that first suggested there might be a swirling ocean lurking under the ice. Today, we know of 95 moons orbiting Jupiter. However, prior to 1979, that number was 13. Voyager discovered 3 new satellites, Phoebe, Metis, and Adrastea, bringing the total to 16 moons by the early 80s. Sadly, we don't have any pictures of them from 1979, though they have been imaged since. The next stop on Voyager's grand tour was Saturn. After 21 months of travel, Voyager 1 arrived on approach to the ring planet in November 1980, closely followed by its companion 9 months later in August 1981. Like I said before, you think rings, you think Saturn. So let's start there. Prior to Voyager's mission, Saturn was believed to have just 5 major rings. However, Voyager 1 showed us that these rings are actually made up of hundreds of thin ringlets. This was the closest flyby any probe had undertaken back then, hence the great detail and learnings. Voyager discovered a ring too, the G ring, and also provided key details about the F ring discovered by Pioneer 2 1 year prior in 1979. Voyager 1 showed us that the F ring is kinked and multi-stranded in nature. It also identified 2 shepherd moons within the F ring, Prometheus and Pandora. This was big news because this discovery confirms scientists' theories that shepherding moons exist around narrow rings to keep ring material in line. Voyager also introduced us to some ghostly features on Saturn's B rings. They appear scattered around the rings in this photo and are said to resemble broad spokes in a wheel. They seem innocent, but they actually caused quite the stir in the scientific community for a while. You see, up until 1980, we thought that Saturn's rings were caused exclusively by gravitational forces. That's all well and good, except these spokes completely fly in the face of that theory. Their existence is not consistent with gravitational orbital mechanics. We still don't know what causes them, but the leading theory involves electrostatic repulsion separating very small dust particles from the main surface of the ring. Sadly, as much as data from Voyager taught us about Saturn's rings, it also taught us that Saturn is losing its rings. Gravity is pulling the rings into the planet, turning them into a kind of dusty rain of ice particles. According to NASA, this could cause Saturn's rings to disappear in 300 million years. Voyager's trip to Saturn raised so many questions that a dedicated mission was mounted in the 90s to exclusively study the ring planet. Cassini probe launched in 1997 and orbited Saturn for 13 years. You can check out a video of mine on what it found here. But we aren't leaving Saturn territory yet. Voyager provided some decisive breakthroughs regarding the planet's moons. We already knew of 14 moons, but Voyager showed us 3 more, bringing the total number at the time up to 17 moons. Let's see what we can learn from Titan and Enceladus. Pioneer 11 was the first probe to image Titan, Saturn's largest moon, and the data it gathered captured the interest of researchers. So Voyager was sent to follow up. It found that Titan had a thick, nitrogen-rich atmosphere, the first and only encounter of such an atmosphere beyond our home planet. Enceladus also turned out to be exceptionally quirky. Take a look at this photo. Enceladus is visible out in the distance with Saturn in the foreground. Now, I know it's tricky to see, but that moon is erupting. Enceladus spews out 300 kilograms of water vapor up to 10,000 kilometers above its surface, 20 times its own diameter. As it orbits Saturn, the frequent plumes of water vapor that erupt leave a donut-shaped cloud that feeds one of Saturn's icy rings. This data was suggested by Voyager data, but it wasn't until we flew Cassini out there that we could confirm it to be true. Further geological data and imaging shows that Enceladus's terrains are an unexpected mixture of old and new. The left side, which appears smooth, is the newer side, and the right side, with the densely packed impact craters, is the older side. This suggests Enceladus is a very geologically active moon, which it wasn't previously thought to be. Before we make our way to the wonky world of Uranus, we have to say goodbye to Voyager 1. After its flyby of Titan and Saturn's rings, its path was bent upward out of the ecliptic plane. From here, the probe headed straight for interstellar space. Of course, it would be another 32 years before it would reach that. But not to worry, Voyager 2 took a slingshot around Saturn instead to propel it on to Uranus and Neptune. These would be the first and only flybys of the planets in human history. 5 years after arriving at Saturn, NASA's Voyager 2 arrived on approach to Uranus in January 1986. At its closest, the probe came within 81,500 kilometers of Uranus's cloud tops. Voyager 2 revealed an absence of visible cloud features in Uranus's atmosphere. Unlike Jupiter and Saturn, Uranus displayed a serene, featureless cloud deck, challenging scientists' preconceptions about the atmospheric dynamics of gas giants. The false color image on the right brings out the subtle differences in the atmosphere of the polar regions, which are tilted on a 98-degree axis. But it was another tilt that stunned Voyager scientists. It was previously unknown whether Uranus had a magnetic field, but Voyager data showed us that not only does Uranus indeed have a magnetic field, it is also tilted at an astonishing 59 degrees. That means its magnetic and rotational poles are not at all in the same place. Until then, it was thought that these poles were always aligned. It certainly is here on Earth. Our magnetic and rotational poles are only shifted by 12 degrees. The stark deviation found on Uranus defied conventional planetary magnetic field models and forced scientists to rethink their assumptions. One side effect of this misalignment of poles is that as the planet spins, its magnetosphere, the space carved out by its magnetic field, wobbles like a poorly thrown football. Scientists still don't know how to model it, but it might look something like this. Voyager 2's observations unveiled more details about the known rings of Uranus, and discovered 2 more. It is the first to capture images of these dark rings, like its outermost ring visible in this photo. The rings are composed of fine dust particles. Voyager 2 also discovered 2 shepherd moons orbiting one of the newly discovered rings, similar to its findings with Saturn's to the F ring. Here they can be seen from 4 million kilometers in a photo from the 21st of January 1986. This mission significantly increased the known count of Uranian moons. Prior to Voyager 2, we only knew about 5 moons orbiting Uranus. Voyager 2 sent us the first ever images of these moons, which you'll see in a second, but it also discovered 11 more moons, bringing the total to 16 moons. Voyager's discovery provided valuable data on their new moon sizes, compositions, and orbital characteristics. Today, the number of known moons stands at 27. Okay, back to Uranus's 5 OG moons. They all appear to be ice rock conglomerates, similar to the moons of Saturn. Oberon and Umbriel, pictured here on the 24th of January 1986, are riddled with impact craters. They seem to have little geologic activity, judging by their old and dark surfaces. Titania, which sits between those two, the 4th furthest from Uranus, is marked by huge fault systems and canyons indicating some degree of geologic and probably tectonic activity in its history. Ariel has the brightest and possibly youngest surface of all the Uranian moons. This photo, taken from just 129,000 kilometers, suggests Ariel underwent geologic activity that led to many fault valleys and extensive flows of icy material at some point in its history. Miranda is the closest of the 5 to the planet, second only in proximity to Puck, the little rocky satellite discovered by Voyager in 1985, and had the most surprising findings. Voyager flew by Miranda on the 4th of January 1986 at a distance of just 30,000 kilometers. This small moon turned out to be a captivating puzzle of geological dynamism shaped by a volatile history. Voyager 2 identified traces of internal melting and sporadic upwelling of icy material, manifesting in extensive canyon-like faults plunging to depths of up to 20 kilometers. The lunar canvas is further adorned with oval, racetrack-shaped features etched like cosmic scratches. Voyager also saw terraced regions, where a mosaic of old and young, bright and dark, and heavily and lightly cratered terrains coexist. The chevron-like characteristics seen here suggest Miranda's original surface was pulled apart and the fragments forcibly re-aggregated back together. 3 weeks later, on the 25th of January, Voyager 2 departed Uranus and snapped this wonderful goodbye shot from 1 million kilometers as it set off to its final planetary target, Neptune. After 3 years of travel at a speed of 54,000 kilometers per hour, Neptune finally came into view. Voyager 2 approached the furthest planet in our solar system on the 25th of August 1989, just over 12 years since it took off from Earth. It produced the first close-up images we've ever received of the giant blue planet, passing only 5,000 kilometers above its north pole, the closest of any flybys. Hydrogen was found to be the most common element in Neptune's atmosphere, although the high abundance of methane is what gives the planet its blue appearance. Voyager 2 measured extraordinary wind speeds in Neptune's atmosphere, with the equatorial winds blowing at speeds reaching almost 1,100 kilometers per hour. These remarkable speeds were yet another surprise and highlighted just how dynamic and ferocious Neptune's weather systems are. Scientists also discovered a massive storm on Neptune, aptly named the Great Dark Spot. This turbulent storm seemed to be rotating counterclockwise, just like the Great Red Spot on Jupiter, and exhibited winds reaching up to 2,400 kilometers per hour, the strongest recorded in the solar system. One NASA analyst, Ken Bollinger, commented on the findings in 1989 saying, "Every day what you see is brand new. Nobody's ever seen it. It's just an incredible feeling. There's changes going on constantly on Neptune that happen very, very fast." Voyager 2 also imaged Neptune's rings for the first time. Up until 1986, scientists suspected the planet might have rings, but couldn't be certain. Intriguingly, the spacecraft identified several partial ring structures, or ring arcs, within Neptune's ring system. These arcs raise questions about the mechanisms responsible for their formation and stability, since they mainly consist of incomplete and dusty rings. A trip to Neptune wouldn't be complete without a quick stopover at its largest moon, Triton. The coldest known planetary body in the solar system, Triton turned out to have a fractured surface, complete with erupting geysers and a pinkish nitrogen ice cap over its southern pole. Scientists also identified dark plumes, which could indicate the possibility of ice volcanoes. Voyager 2 also discovered 6 new moons orbiting Neptune, including these. As Voyager 2 turned around to snap one last look at Neptune and Triton, it had officially completed its grand tour. Neptune's gravity bent its path downward out of the ecliptic plane. From here, it continued its voyage into interstellar space, just like its counterpart Voyager 1 had done 9 years before. Speaking of Voyager 1, let's see where it's ended up since we last checked in 1980. 1 year after Voyager 2 finished up with Neptune, Voyager 1 was already about 6 billion kilometers away. in order to conserve power for the long journey into interstellar space, scientists were going to switch off its cameras forever. However, on the advice of Carl Sagan, the team decided to turn the camera around for one final picture, a look back at home and how far we had come. And so, on the 14th of February 1990, Voyager 1 took the most remote selfie in history from 6 billion kilometers away. The result? The infamous pale blue dot photo. In the immortal words of Carl Sagan himself, look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines. Every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there on a mote of dust suspended in a sunbeam. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. This sentiment rings with as much power today as it did 33 years ago. But what came next? What did the Voyager probe see and do in interstellar space? In 1981, Voyager 1 escaped the ecliptic, which is the Earth's plane of orbit around the Sun, heading 35 degrees to the north. Voyager 2 later went under the ecliptic, heading 48 degrees to the south. However, this was barely the start of the Voyager's journeys. To reach interstellar space, the probes would have to traverse the termination shock, a region in which hypersonic solar winds run into fierce resistance from the interstellar wind. Beyond the termination shock, the Voyagers would encounter the heliosheath, where slowing solar winds pile up, becoming denser and hotter, followed by the heliopause, the final boundary between the heliosphere and interstellar space. But in spite of what you may think, the start of the interstellar medium doesn't actually mark the end of our solar system. Indeed, it will be another 300 years until Voyager 1 reaches the Oort cloud, the vast region of billions of icy planetesimals that surround our solar system like a bubble, and another 30,000 years until it exits the cloud, leaving our solar system forever. When the Voyagers travelled through the heliosheath, they made an incredible discovery. Because the Sun's magnetic field spins in opposite directions on its north and south poles, the spin creates a ripple where they meet called the heliospheric current sheet, sort of like the rings created by dropping a stone in water. However, when this sheet reaches the termination shock, it compresses, as though the ripples were hitting the edge of a pool. The Voyager probes discovered that after the termination shock, these stacked up ripples form magnetic bubbles. This means the boundary of the heliosheath is not as smooth and clear-cut as scientists thought. Instead, it is a fluctuating and magnetically bubbly environment. This messy finding has prompted a complete revision of our model of the heliosheath. On the 25th of July 2012, the Voyager 1 space probe became the first man-made object to leave the Sun's heliosphere and enter interstellar space. It was traveling at an incredible speed of 540 million kilometers per year, or 3.6 astronomical units, an astronomical unit being the distance between Earth and the Sun. The distance at which Voyager 1 crossed the heliopause was about 120 astronomical units from the Sun, which itself was a revelation. It was unknown where, exactly, the heliopause occurred. Funnily enough, some early models put it as close as Jupiter, and others much further. Remember, the heliopause is the boundary where the sun's solar wind is stopped by its collision with the interstellar medium, kind of like the crashing of two powerful bodies of water against each other. Solar wind is the steady stream of charged particles, such as electrons, protons, and alpha particles, that come from the sun's outer layer. The interstellar medium, by contrast, consists of charged particles, gases, and cosmic dust left over from the Big Bang and other ancient supernovae. When these charged streams hit each other, they change course and form a region of equilibrium called the heliopause boundary. At first, NASA wasn't sure if Voyager 1 had truly crossed the heliopause and entered interstellar space. As models predicted, the probe's plasma wave detector found a massive increase in plasma density, 80 times what it had registered in the outer heliosheath, and a spike in galactic cosmic rays. But something strange didn't happen that left scientists baffled. After crossing the heliopause, Voyager 1 detected no change in the ambient magnetic field. Why was that so surprising? Well, theoretical models assumed that the ambient magnetic orientation would change in a region dominated by the magnetic fields of other stars. But remarkably, Voyager 1 detected no discernible change in the ambient magnetism. NASA was so confused that they waited nearly a year before announcing that Voyager 1 had, in fact, entered interstellar space. On the 5th of November 2018, Voyager 2, traveling at the slightly slower speed of 490 million kilometers, or 3.3 astronomical units per year, joined Voyager 1 in becoming the second man-made object to enter interstellar space. The crossing also occurred 120 astronomical units from the Sun, and like the Voyager 1 6 years earlier, the probe detected no change in the ambient magnetic field. But something else surprised scientists. You see, the Sun goes through 11-year solar cycles, during which its activity waxes and wanes. Voyager 2's crossing occurred at a time when solar winds were peaking. Models predicted that the size of the heliosphere would fluctuate with the solar cycle, meaning it would have been expanding when Voyager 2 made its crossing. Yet, Voyager 2 crossed the heliopause at exactly the same distance Voyager 1 had 6 years prior, meaning our models were wrong. Like the magnetometer finding, this demonstrated the value of testing theoretical models with field data. We now suspect the boundary between the heliosphere and interstellar medium is much more twisted and filled with fluctuations than prior models proposed. One leading idea is that our Sun emerged billions of years ago from a hot and heavily ionized region following the explosion of one or more supernovae, and that magnetic turbulence persists to this day near the heliopause. If so, the probes will likely encounter a different magnetic orientation as they travel further away, but their instruments will probably be long dark by that time. After all, the probes are already starting to fail. In early May 2022, Voyager 1's signal went strange. Imagine you are a NASA scientist. You arrive at your computer for the day and begin looking through the Voyager 1 telemetry data. Voyager 1 sends back status updates about its systems, letting you know whether everything is functioning normally. It takes 22 hours now for a signal to reach Earth from Voyager 1, so communication is a little slow between you and the spacecraft you're overseeing. Currently, it's more like sending letters than text. However, today something is wrong. The information it has sent you is gobbledygook. Instead of precise data explaining exactly what Voyager 1's thrusters are doing and what orientation it believes itself to be at, you get long strings of zeros or 377s. The information does not make sense. It suggests that Voyager is doing things and pointing directions that it cannot be. You quickly check your computer again. Yes, you did just receive a signal from Voyager 1. So its antenna must be pointing towards you, the same as it always has. It cannot be pointing in the strange directions it is claiming, or you would not be getting a signal at all. And not only are you receiving the signal, but it's at the exact same strength too, so it has definitely not changed direction. And ping, onto your computer comes Voyager 1's latest science data. Strangely enough, this is all normal. While over the years Voyager 1 has had to turn off 5 of its 11 pieces of scientific equipment, and a further 2 have stopped working due to general degradation, the remaining 4 continue to take readings about the interstellar medium, magnetic fields, and cosmic rays. Nothing here is garbled in any way. You check the other systems. Voyager 1's power supplies are a little low, but that's to be expected. The plutonium oxide that fills its 3 generators have a half-life of 87 years, but Voyager 1 has been traveling for 45 now. It's no wonder the efficiency has started to decline. In fact, the experts believe that Voyager 1 will not last past 2025. But that's some time away. It does not explain what is happening now. After checking its other systems, it is just one that is behaving strangely. The AACS, the Attitude, Articulation and Control System. This computer is one of 3 on Voyager 1. And remember, its job is to make sure the spacecraft's large 3-meter antenna continues to point towards Earth. This AACS has stopped sending coherent data. You lean back, puzzled. The situation is not as bad as you might have thought, but it is troubling. It's kind of like receiving post from a postman who says hello to you every morning, only for some reason he starts speaking another language one day. The packages he delivers are still the same, and they've arrived at the same address. It's just the words the man speaks make no sense to you anymore. To further compound the strangeness, Voyager 1 doesn't think that anything is wrong with it at all. The spacecraft comes equipped with emergency safe mode settings that it can go into if it detects that anything is not working the way it ought to be. Essentially, these involve powering down until scientists can figure out what's wrong with it. And these have not activated. So Voyager 1 believes that all its systems are working the way they should be. The data is given, the scene is set. This was the question that NASA engineers faced in mid-2022. A single fault like this might not seem like a big deal, but it hints at something potentially wrong with further systems. And if that is true, it might spell an end to the whole mission. Voyager 1 is, by now, 23.8 billion kilometers away from you. Your solution will have to be made via deduction, alongside careful 22-hour each-way questions and answers with the faulty spacecraft. By evaluating the rest of the systems and finding them normal, you can rule out some of the more unusual explanations. No, this probably is not the work of aliens trying to mess with you. Although NASA scientists were open to the idea of the Voyager probes maybe one day being picked up by alien life, as evidenced by the golden discs installed on the probes filled with messages about us for aliens to read if ever they stumbled across it, this was more of a symbolic gesture. Besides, it seems that this would be a strange way for aliens to communicate with us. And no, the laws of physics have not broken down. Voyager 1 has not entered a wormhole that is skewing where it thinks it is, while still somehow getting the signal back to you. Given that the scientific data all appears to be providing normal readouts, it's much more likely that the problem lies with the AACS itself. For 4 months, scientists and engineers gently prod and examine Voyager 1. Testing theory after theory and trying to come up with a solution that fixes things without causing any further damage in the process. They could switch over to a backup system. It would not be the first time they'd started using a new computer on Voyager 1 after the old one stopped working. Voyager 1 is built with redundancies. This isn't even the first AACS computer that's been used. A previous one became defective a while ago. They also contemplate just leaving things be. After all, the science data is still coming in. Would it be the end of the world if Voyager 1 simply carried on speaking garbled messages? Perhaps this could be the new normal. Except it implies that a deeper problem is being overlooked. Can you figure out what was going wrong? If you can, perhaps NASA should look into hiring you. It turns out that in the intense, radiation-filled environment of interstellar space, something had made Voyager decide to start using that older, broken AACS computer to send data back to Earth. Because of the faults in this computer, the data had become corrupted, resulting in the strange numbers. So actually, in this case, the fix was easy. All NASA had to do to fix it was to ask Voyager to start using the right computer again. Once Voyager 1 did that, the problem was resolved. Well, I say easy, and I say resolved. It still took a couple of months for Voyager 1 to start behaving normally again, and even then, in November 2023, another of Voyager's onboard computers, this time the Flight Data Subsystem, underwent a similar problem and became unable to send home usable science and engineering data. It took until June 2024 until that problem was fully resolved. Voyager 1 is an old ship now. As it continues to travel through interstellar space, it may encounter more and more faults. In July 2023, a routine series of commands sent to Voyager 2 caused the probe to orient its antenna 2 degrees away from Earth. This seemingly small divergence was enough that over the massive distances involved, NASA completely lost the ability to talk to Voyager 2 or hear back from the probe. It was only through sending out an interstellar shout from the Deep Space Network facility in Canberra, Australia, that a signal was able to be sent to Voyager 2, telling it to reorient itself back towards Earth. The 37 hours of waiting for the shout to arrive and for the probe to signal back that it had followed the command must have been tense for NASA personnel. The probe could have been lost forever. One way or another, it's inevitable that the Voyager probes will stop transmitting back to Earth. Whether through error or malfunction, or simply running out of power, the end is unavoidable, and the curtain will fall on this incredible mission. But even then, the twin probes are just beginning their cosmic journeys. In 40,000 years, Voyager 1 will likely drift towards a star in the Camelopardalis constellation, while Voyager 2 will pass 1.7 light-years from the star Ross 248. In 296,000 years, it will pass 4.3 light-years from Sirius. These small, intrepid probes will likely outlast the Earth itself as they continue their solitary wanderings across the Milky Way. And if by chance they encounter intelligent life in one of the far reaches of our galaxy, they will be a testament to mankind's ingenuity and resilience. Remember I mentioned that on each of the probes was a message to the stars? These golden audio-visual discs are called the Golden Record and carry photographs of Earth and its many life forms, the sounds of whales and of babies crying, music by Mozart and Chuck Berry, and dozens of indigenous peoples and greetings in 55 languages. They would offer a distant stranger a glimpse of who we are and what life on Earth is like. As for us, we must say goodbye to these old familiar friends and continue our own lives here on Earth. Hopefully the Voyager mission will not be our last brush with the stars, but only the beginning. Is the universe inescapable? If we were to conquer the limitations of light speed and were to travel to space's furthest edge, what might we find? Just more space? Infinite planets and planetary systems? Or would we somehow come back to where we started? Amazingly, according to scientists, all of these are possible, but which one is correct comes down to the nature of that unseen world all around us. I'm Alex McColgan and you're watching Astrum. Join me today as we continue our series exploring the unseen world of 4D space and discuss possible answers to the question, what is the shape of the universe itself? But first, let's begin by talking about infinity. You are likely already familiar with infinity. In maths, it is the concept of a number so large it cannot possibly be beaten. Of course, no such number exists. For any number you can name, I could come up with a number that is at least one larger than it. But in a way, that's sort of the point. In infinity, there is always another number. And when it comes to our universe, we have so far discovered no edges. There may always be another star or planet. An infinite universe is a little mind-boggling for us. We live in a very finite world with edges and endings. So the idea that there might be literally infinite more planets out there is a little bewildering. However, as we develop more and more powerful telescopes, and pushed back the darkness further and further at the edges of what we can observe in our universe, all we are finding is that even the darkest patches of the night sky are turning out to be brimming with stars. So increasingly, an infinite universe might be something we are forced to contemplate. But that is not to say that just because the universe is infinite, there are not a finite number of things in it. That may sound a little counterintuitive, but let me show you what I mean. Believe it or not, there are different kinds of infinity when it comes to our universe. 3 possible scenarios could be true: a flat universe, a spherical one, or a hyperbolic universe. Allow me to explain. In a flat universe, if we were to form a grid to broadly represent reality, everything would seem fairly standard. All the lines would either be parallel to each other or perpendicular. An infinite universe of this variety would simply extend outwards in all directions forever and ever. This is a little boring, so I won't spend too much time on it. However, this is a lot like we perceive the universe to be. For the most part, all lines of direction appear straight to us. We can distinctly see the planets and stars around us, and we notice no real curving or warping. However, this is not the only way that the lines can be drawn. Consider for a moment a black hole. You may immediately notice the strange rings that appear to run around its equator, as well as across the top of it and along the bottom. This is something of an illusion. There are no rings across the top or bottom of this black hole. What you are seeing is the equatorial ring that's on the other side of the black hole. However, due to the powerful gravity of the black hole, the light that is hitting it is not bouncing off upwards or downwards into space. Instead, the rays are curving towards us as the black hole's gravity pulls them in. You are seeing the top and bottom of the ring at the same time. Light being bent by gravity. What do I mean by that? Actually, this is an excellent example of our second kind of universe. In a flat universe, all the lines that make up reality are fairly straight. But what if we were to come up with a rule? All the lines must instead curve towards each other. There is only one way such a universe could be drawn, and that is in a sphere. Consider trying to draw 2 parallel lines on a sphere. You might start off well, but will quickly realize that your task is impossible. All lines would converge towards each other, intersecting at least twice as they return back to where they started. What would a universe that was based on these kind of lines look like? Essentially, rather than going in the straight line you thought you were going in, you actually would be traveling in a massive curve. It's a bit like those computer games where you travel off one end of the screen only to reappear from the other side. In a spherical universe, you could travel infinitely, but ultimately you would only end up arriving back where you started. With a powerful enough telescope, and if light were to travel a whole lot faster all of a sudden, it would be possible to look at the back of your own head. This kind of universe contains a finite amount of things, but it appears infinite because you just keep bumping into the same things infinite times. Thanks to objects like black holes and powerful stars, we do indeed have evidence that our reality sometimes is a curved, spherical one, at least near large bodies of mass. The inside of a black hole's event horizon is this kind of infinite space. No matter what path you take, you can never get out of it. However, let's consider our last example, the hyperbolic universe. This one is the hardest to visualize, but the idea is simple. Instead of having all lines remain parallel or move towards each other, every line must move away from everything. Drawing this is inherently tricky because everything keeps getting wider exponentially. The only way you can do that is to either buckle your nice flat disc until it becomes something like this, or warp what you are seeing like this. All of the objects in this image are squares. However, they are squares that are obeying our rule that all their lines must be diverging away from each other. This leads to the very strange situation where you can have 5 squares all meeting up at a corner instead of the usual 3 that is possible in normal 2D space. Alright, this seems a little confusing. What does it mean if space is hyperbolic? Well, let's consider what it is we are curving around. You might have noticed when we talked about our spherical shape that there must be something we are curving around. That direction of curvature is in regards to time. Imagine, if you will, a series of timelines. We go a little more in depth with the interplay between space and time in my last video, which I would really recommend you check out. But for now, just remember for this model that objects in time move forward along their timelines in the direction of up, or the future. If they move left or right, they are moving through space, getting closer to each other. If we introduce a large mass into this model, it warps the timelines. Now, if you were a small object traveling along one of those arrows that got too close to the mass, suddenly your path of travel no longer goes directly up towards the future. It pulls you left or right towards the mass. There are several reasons for this, but the essential thing to recognize here is that now your straight path towards the future pulls you in towards the planet, so you'll have to accelerate away from it just to stay on a straight path. In a nutshell, you are experiencing gravitational pull. Even the planet is affected by this. The atoms on either side of it are squeezed towards the center of mass, as if it were being forced down a narrow tube by giant invisible hands. Let's get back to hyperbolic space. In this model, the opposite thing is happening. All lines are moving away from each other. We could represent this by curving space and letting our timelines be straight, which is nice because it captures the idea that from your perspective, your time is always ticking forward normally. But let's warp this slightly so that space is flat. It's all a matter of perspective after all. Here, parallel lines are also impossible, but this time, rather than converging, all parallel lines diverge more and more. Everything moves further and further apart. Why does that sound familiar? It is because that is what the universe is doing. This is not noticeable within a galaxy, where there is enough mass and gravity to keep everything together. However, from what we can see of the universe as a whole, every galaxy is moving away from every other galaxy. Scientists try to explain that with dark energy, but maybe all that is happening is that the universe is just naturally hyperbolic in its shape. So what would that mean if the universe really was hyperbolic? It would mean that the universe was really infinite. The flat space we looked at was infinite. For each light year you traveled out, you discover another light year's worth of space. However, with hyperbolic space, you discover more than another light year's worth of space. It's like opening infinite doors, except inside each door are two new ones. The possibilities would be far more endless, far more infinite than in just regular flat space models. But also, it means that given enough time, the rest of the universe would drift away from us until our galaxy was all that was left. Scientists have looked across the universe, however, have not noticed this hyperbolic space in action. In fact, things all look pretty flat, so perhaps flat space is the correct answer. Yet, this still leaves room to me for hyperbolic space to be the default. After all, if matter is curving space towards it, and the universe appears flat, it would make sense that the universe was curved in the inverse, at least to some degree. Perhaps all three models are true. Perhaps the universe is by default hyperbolic, but mass brings it together in such a way that it perfectly offsets the inverse curves of the universe to the point where everything appears flat. There certainly seems to be some evidence that this is the case, but it's very difficult to know for sure. Which model do you think is correct? Or maybe you feel that we do not live in an infinite universe at all? Please leave a comment down below to tell me what you think. But for now, just remember, the unseen world might be a lot more influential on our universe than we are currently aware of. In ancient times, tribes of humans would huddle around the flickering light of a solitary campfire, wondering about what might lurk out in the darkness. And in that respect, things haven't changed. Our campfires might be larger now, our vision reaching across the globe and even further, out to the very edges of the observable universe thanks to telescopes like the James Webb. And yet, there is always an edge where darkness falls and it's left to our imaginations to fill what lies beyond it. The observable universe's edge is an impenetrable barrier. It is the section of space that is accelerating away from us so quickly, nothing, not even light, can approach us from beyond that line, and so nothing beyond it can interact with us causally. So, unlike the darkness that came before, whatever lay on the other side of this particular edge seemed destined to remain a mystery because it could never reach us, and we could never reach it. Or so we thought. But in 2008, hundreds of galaxy clusters were analysed to be drifting towards a section of that edge, faster than science could account for, almost like something beyond that point was pulling them, or had once pulled them, with a reach that extends across billions of light years. Something massive lurking beyond that final dark. This drift of galaxy clusters that spans across the universe has a name: Dark Flow. What do we know about it? What could be causing it? And what are its ramifications on cosmology? I'm Alex McColgan and you're watching Astrum. Today let's dive into the mystery of Dark Flow and its model-breaking implications for our theories concerning the origin of the universe. Dark Flow is a controversial topic, so we'll start with what we know for sure. In 2001, the Wilkinson Microwave Anisotropy Probe was launched by NASA to map out the cosmic microwave background radiation, the fizzling echoes of the Big Bang itself that quietly radiate across all of space, to help us understand better the features of our universe. This map was completed in 2010, although it released its data in installments before that point, and was hugely influential on cosmology as it helped scientists to answer questions like how flat was the universe, or how much of the universe is made up of physical matter compared to dark matter or dark energy. Alexander Kashlinsky was one scientist eager to get his hands on this data. Leading a team of researchers at the NASA Goddard Space Flight Center, Alexander was excited to try to compare the cosmic background radiation map with the motion of galaxy clusters to see if there were any interesting patterns in the flow being witnessed. It was a difficult task. To tackle it, Kashlinsky and his team were taking advantage of something called the kinematic Sunyaev-Zeldovich effect, which was very tiny. This technique essentially makes use of the fact that when cosmic background radiation passes through a high-energy galaxy cluster, it gains a little of that energy. This works whether the galaxy cluster is very hot, thus heating up the cooler cosmic radiation, or whether the galaxy cluster is moving quickly and thus has a lot of kinetic energy to impart. Either way, the radiation gets a little boost, and you can use this information to infer things about the existence or motion of galaxy clusters. The problem is, this boost is so tiny, it's necessary to use multiple galaxy clusters and some statistical calculations to notice it at all. The researchers needed a detailed enough map of the CMB to then be able to compare 1,000 known galaxy clusters against to try to find movement. And to their surprise, they found a pattern. A massive bulk flow of galaxy clusters in comparison to the CMB, stretching 2.5 billion light years away from us across the universe, with clusters moving between 600 to 1,000 kilometers per second in the direction of the constellations Centaurus and Hydra. The mystery is, there is nothing out there to account for this motion. Some massive source, or sources, of gravity presumably had to be pulling these galaxies towards them, but it was outside of our vision, which led to the implication that a particularly large source of mass likely had to exist at or beyond the edge of our universe, just out of sight. And this is a very controversial idea. But first, is it even possible for something beyond the edge of the universe to influence us gravitationally? You might think the answer would be no. As I said in the beginning of this video, nothing that exists out there can now affect us causally, and we can't affect anything out there. That's just what happens when space expands between 2 points so quickly that the expansion outpaces the speed of light. You lose the ability to interact, even gravitationally. I talk about this in more detail in my video on the end of the universe. But there is a loophole if you do that interacting before a period of time in the Big Bang known as the cosmic inflation. For those of you unfamiliar with this concept, essentially, scientists back in the 1970s were wondering why most parts of the universe looked very flat and very much the same in terms of temperature and distribution of mass if you zoomed out enough, even parts that never interacted with each other before. For instance, the edge of our universe to our left and the edge to our right are very similar to each other, even when there was no reason this should necessarily be so, as they've never met. This idea is known as the horizon problem. An American physicist known as Alan Guth realized that the problems raised by this mystery all went away if at the start of the universe everything did interact with each other, evening out like a mixture of blue and red dye in water when shaken around enough. But for that to be the case, and for everything in the universe to then explode out to where it is now, a period of really fast expansion of space was needed somewhere at the start, in addition to the already fast Big Bang itself. It's a little uncertain, but physicists have placed this super expansion as taking place just after the Big Bang began, and lasting only 10 to the power minus 33 seconds, which is not very long. But in that time, it would have expanded by a factor of 10 to the power 26 times, which is insane. This mind-bogglingly fast expansion is akin to going from the size of a bacterium to the size of the Milky Way galaxy, all in a billionth of a trillionth of a trillionth of a second. The nice thing added by having this cosmic expansion event as part of the Big Bang model is that it allows you to explain how everything had a chance to mingle before in the time of the early universe, even the parts that are now unreachable to each other. There are even some very respected theories about how it came about, involving terms like scalar fields and false vacuum state, but that's a little heavy on the physics side and isn't really needed for this video. But the takeaway is this: dark flow could be explained. In that pre-inflationary period where matter wasn't even coalesced into atoms yet, there was a particularly dense section of the wider universe that our particular patch of observable universe got tugged towards on account of it having so much gravity. Cosmic inflation could then have happened, pulling the powerful mass far away from our observable universe to the point where we are no longer gravitationally affected by it. But because things in motion tend to remain in motion, the galaxy clusters given that initial pull are now simply drifting along in that same direction, going with the cosmic flow. But as I said, this is controversial for two main reasons. Firstly, dark flow needs a particularly large amount of mass to exist just outside our universe for it to work and make sense. There have to be far more stars out there, concentrated far more densely than our models currently predict, which flies in the face of the whole reason Alan Guth came up with the cosmic inflation in the first place: uniformity. The universe as we see it is uniform. It is roughly homogeneous, which means that mass is distributed fairly evenly no matter where you look. It is also isotropic, meaning that if you add up all the velocities of everything moving in the universe, it all cancels out. Dark flow upsets this whole idea. It suggests that just beyond the visible horizon, things suddenly stop being so uniform. That dense amount of mass is still in existence, we just can't see it. And that's an idea that's a little out there. It's an idea that raises a whole lot of questions. If the universe is not actually uniform beyond our horizon, did we just get cosmically lucky to find ourselves in an exceptionally flat bit? What does that mean for our theories about the formation of the universe itself and cosmic inflation if the reason inflation exists is to explain a homogenized universe that isn't actually that homogeneous. The second reason that Darkflow is so controversial though is that it might not exist at all. Kashlinski's NASA team might be convinced of it, but ESA's Planck team double-checked the existence of Darkflow using an even more detailed CMB map, one provided by their own, more advanced Planck probe, which launched in 2009, 8 years after WMAP. After looking through 1,000 galaxy clusters, the Planck team claimed to see no signs of Darkflow at all. But Kashlinski and his team then took a look at the Planck data, and they claim that they do see signs of Darkflow. So there's still a lot of debate on the issue. Kashlinski and his team announced in a paper that they would be doing an even more in-depth analysis using Planck and WMAP data, intending to establish more conclusive proof, but this has yet to be released. Until we have better proof or indications of this, it makes sense to assume Darkflow isn't a thing, and there is no boogeyman lurking just beyond the edge of the light that billions of years ago dragged thousands of proto-galaxies towards it. But as with all unknowns, it does make you wonder. Science does not really care about what's the most convenient answer. Truth is the truth, whether complicated or simple. Perhaps one day we'll somehow find the answer once and for all to what lies beyond the visible universe and whether Darkflow is real. But then all that will happen is the darkness will simply retreat a little further and the next cosmic boundary will appear, causing us to wonder once more. There is always more to know, and humanity's hunger for knowledge and discovery will never cease. Thanks for watching. Making this video required some long-term planning and work, which we were only able to do thanks to the consistency and sustainability of your memberships as Astromnauts on Patreon. A huge thank you to everyone who has signed up, and if you'd like us to make more videos like this, you can join with the link down below. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrom content. I'll see you next time.